All right, today I'm going to have a video lecture on which I typically would have done a PowerPoint for you guys with classification of matter. I've already asked you to do the 5 assignments that are found in CK12. Many of you have done them and have gotten 100% on all of them. Great job. If you don't have 100% on each of those 5 assignments, then please go back to CK12 and do those module units, those specific assignments, and redo those questions until you got 100% so you got a good review of the topics. For those of you that have already done that, this lecture I'm going to try to go over fairly quickly because this is just hitting upon those key concepts that you should have gathered in the CK12 unit. All right, so we have matter. Again, matter is anything that has mass and takes up space. Okay, therefore it has mass and volume. So anything that has mass and has volume is classified as matter. Now we can further break that matter down into different subclasses. Okay, the first being, is it a pure substance or is it a mixture? If it is a pure substance, each of the particles in the material is exactly the same. So if I were to draw a container and the atoms of a substance in that container, if all the particles are exactly the same, it is a pure substance. If you have a container and then we have different, now these are different colored spheres which represent different colored atoms. If you see within that particle, if you have different particles, then that would be classified as a mixture. Okay? If all the particles are the same, then it is a pure substance. Now let's do one that's a little bit harder that maybe some of you might struggle with the identification of that. So let's say I draw this as my okay. Would this be a picture of a pure substance or a mixture? Now students right away want to say that it's a mixture because not all of the spheres, the atoms in this picture, are exactly the same. But actually, if you look at each particle, you'll notice that each particle contains an atom that has a black sphere, and then it's got 2 other atoms attached to it that are red spheres. Every single particle in this closed container is exactly the same. So this is indeed an example of a pure substance. Now the difference between these 2 pictures here is that up above, all of the atoms are exactly the same. So this would be an example of an element where everything in the box is the same type of atom. Here we have different types of atoms and they're bonded together, and those are examples of compounds. So this right here might be an example of the compound water, H2O, where we've got 2 hydrogens, the red spheres, connected to the 1 oxygen atom. And here this might be a picture of a gas like helium, the element helium, where each single atom is exactly the same type of atom, and therefore is an element of helium. If your container contains different pictures of different particles identified as either different shades or sizes or colors, then it is a mixture. Now, mixtures can further be broken down into homogeneous and heterogeneous. Homogeneous means uniform, which means when we look at it, it all looks exactly the same. Salt water would be an example of a homogeneous mixture, where when you look at salt water, if you mix some salt into water and stir it until it dissolves, you'll see that there is only one layer of material. It's all uniform. Heterogeneous means it's more than one, sometimes more than one state. You can physically see that there's more than one state. There's layers to it. There's different particles possessed in it. And then it's further broken down into suspension and colloids, which we'll take a look at in the next slide. So examples of homogeneous solutions would be Kool-Aid, where it's uniform throughout. When I have a picture of Kool-Aid, the very top part of the solution tastes exactly the same as the bottom part. It's evenly mixed, evenly distributed. Okay? Heterogeneous would be where we have different layers potentially, like pond water. We can see different phase or different material. Okay, you might see twigs, debris, tadpoles, different types of organisms or things in it. That's a suspension. A colloid is something where it doesn't separate out, but we have something called the Tyndall effect. And I'm going to show you now in a second what that looks like. Here are examples of mixtures. So I look at this slide here. Okay, I am looking at A, B, and C. A is an example of a homogeneous solution. All homogeneous mixtures are solutions. You can see that it's uniform throughout. You can't see any difference between them. And we'll get in a second is how I can tell that versus a colloid. This is more than likely an example of a heterogeneous. And this is an example of a colloid. Okay, and then here is an example of a suspension where it's much more opaque. You can't really see through it. And over time, this suspension, C became B, where it begins to settle out. The difference between a suspension and a colloid is a suspension will settle out if you give it time. If on the bottle it says shake before you use or shake before you pour on your cereal or whatever, those are examples of suspensions. Okay, here is muddy pond water that was in a jar, shaken, and then it was let to sit. Because we see two different layers, this is an example of a suspension. Now, if I pour that suspension through a filter, what's going to be left over is this top part, which more than likely, after it is separated out, the top part still probably contains some small particles of sediment, but because they're so small they stay in the solution, that is an example of a colloid. So a colloid, the difference between really a colloid and a suspension is size of particles. These guys have smaller particles, and therefore they stay in the solution. A suspension, the particles are so big that they settle out of the solution, and that is an example of a suspension. Italian salad dressing is a classic suspension because you have to shake it up. And when you let it sit, it starts to separate, and that is an example of a suspension. So, how can I tell the difference between a solution and a colloid? Because both of them, neither one, will settle out. And the key way I can tell the difference between a solution and a colloid, a suspension will settle out, is called the Tyndall effect. And many of you guys have already seen this before. When you shine light into a solution, the light will pass right through. You will see no scattering of the light beam. You cannot see the light beam travel through the material. That is called a negative Tyndall effect. Which means if we don't see the scattering of light, it is a solution. The particles inside of there are so small that the light will not bounce off of, and the light beam will travel right through it. That is a solution. If you can see the light beam travel through the material, now the particles inside of here are big enough that they will scatter light. The light beam will hit it and scatter, and we'll be able to see the beam travel through the material, and that is a colloid. This is an example of a positive Tyndall effect. So how do we tell the difference between a solution and a colloid? We do the Tyndall effect and see if we can see light travel through it. So here we can see different colloids in real life where we can see beams of light traveling through the air, probably because there's dust or smoke in the air, or fog during the morning. You can see light traveling through it. Fog at night with head beams through your vehicle car lights. Those are all examples of colloids and a positive Tyndall effect. All right, so here is a quick table that you might find very useful in the different properties. Solutions are always homogeneous. They are uniform. They are evenly distributed. They cannot be filtered because the particles are too small. They do not settle out because the particles are too small. And there's no Tyndall effect because the particles are too small. In a colloid, it's heterogeneous. Usually because it's opaque, you can tell there's more than one thing in the liquid. You cannot filter it because the particles are too small. They won't settle out because they're too small. But they are large enough that the particles will scatter light and therefore have a positive Tyndall effect. Suspensions, the particles are so big that we can filter them. They will settle out because they're so big. And the Tyndall effect, this is actually incorrect. It should be a positive Tyndall effect as well because the particles are so big that they'll scatter light. The issue with the Tyndall effect is it usually will cause light not to travel through it. And so we usually don't talk too much about the Tyndall effect with suspensions. Because they settle out, it's pretty easy to tell when you have a suspension. All right, turning page. How do we separate mixtures? And that's going to be an important concept when we get into the unknown powders lab, which we're going to do next week. But for the most part, there's a couple different techniques we can utilize in this class to be able to separate them. So let's take a look at those. The first here is when they tend to layer, if you have oil and water. When they form multiple layers or they have different densities. Okay, in this object here, when I drew this picture, I've got two different liquids, they separate out. Who is the more dense liquid, A or B? B is more dense. And therefore I can simply pour off A first, and we can simply do what's called decanting. We can decant off the oil layer from the water layer if we just simply pour it. Or I can take a pipette and I can suck up A off the top of B. Are different ways we could separate liquids that have varying densities and are not soluble in each other. Another technique is distillation, where I have two liquids, okay, let's say alcohol and water, but they're soluble in each other, and therefore they do not form layers. However, the water and alcohol probably have different boiling points. So what we can do is we can separate them by their boiling points. So I can pour the material into a flask and heat it, send it through a cold condensing tube, and what drips out, so what happens is the steam comes up, it goes through this tube. Because cold water is running around the outside of it, it cools the liquid and it recondenses. And what's dripping out of here is the liquid that has the lowest boiling point. So the first liquid comes off the mixture first because it boils off of the material first. And now I've got the pure first liquid that comes off of it. A great application of this is for those who'd like to watch those moonshine shows. Moonshine is an example of where they make the material using corn or other materials and sugar and water. They let it ferment. They boil off and the alcohol comes off first. And what we get over here coming out of it in the condensing tube is mostly straight alcohol, which is moonshine. And if they let it boil longer, then eventually water starts to come off of it. And then there's less alcohol and there's more water. And now it's not as strong of an alcohol solution. Okay? So if you have multiple liquids that are soluble in each other, we can use their different boiling points to separate them. All right, lastly, I guess what I should have done is the third mechanism, which is a filtration. So if I've got a mixture where I have a liquid and I've got some solid, I could pour that through a funnel with a piece of filter paper, and the solid will be collected in the funnel and the liquid will drip through. So we can also use filtration. We can filter mixtures if we have a liquid and an insoluble solid that doesn't dissolve in it. So those are three different possible techniques we could utilize to be able to separate mixtures. The last thing I want to talk about is how do we differentiate between elements and compounds. So now we are looking at pure substances. The key thing with elements and compounds is elements cannot be broken down. Compounds can be broken down. And the most common way we can break apart different compounds is we can utilize heat. For example, if I have a compound called mercury oxide, I can heat mercury oxide and it will separate into mercury and oxygen. And specifically, oxygen by itself forms in double pairs, which we'll later talk about. So the key thing is separate those two by simply heating them. So again, a compound is where we have two different types of elements bonded together and will be symbolized by different colored spheres. We can also separate things like water using electricity. So something called electrolysis. And we can separate the hydrogen and the oxygen into separate entities by using electricity to separate them. So these are two basic techniques that we can use to separate a compound into its individual elements. So again, a compound will have two different types of atoms bonded together. Elements, they're all exactly the same. Okay? Elements we cannot break down by simple means, chemical means. Compounds we can. That's the big difference. So here's an example of electrolysis where we use electrical current to separate the hydrogen and the oxygen. And you'll notice in this picture that on one side there's one gas, the hydrogen, on the other side there's the oxygen. You'll notice how they're at different levels. We have more gas collected here than on the left side. If you want to realize why there's a difference in volume heights, and hopefully you're thinking, what is the chemical formula of water? H2O. So when this guy separates, we're getting 2 hydrogen atoms for every 1 oxygen atom. And therefore, we're going to collect twice as much gas on the hydrogen side as the oxygen side when these guys split and separate. All right. Last slide for this lecture is looking at particulate representations. What I'd like you to do is look at this first example here, number 1, and I'd like you to tell me, is this a pure substance or is this a mixture? Hopefully you're saying pure substance. Why is it a pure substance? Well, if we look at it, each of the spheres are exactly the same. Second question for number 1, is this an element or is this a compound? Hopefully you said element, because every single particle here, every single atom is exactly the same. Okay? Now there's a bond here, so this is an example of a molecule because they're bonded together, but they're the same atom bonded to itself. So this is an example of an element, specifically a diatomic element, where it exists in 2 atoms bonded together. But this is indeed a pure substance, and it is an element because we don't have different types of atoms. Let's look at picture number 2. Okay, is this a pure substance or is this a mixture? All right, apologize. I had a phone call I had to click, so I paused the presentation. So in number 2 here, would you classify this as a pure substance or would you classify this as a mixture? Now, this is an example of a mixture because if I look at the particles, they're not exactly the same. One has got 2 blue spheres and one's got 2 red spheres bonded together. Okay? Second question, now this is a mixture. Is this homogeneous or is this heterogeneous? And the answer is it's homogeneous because you'll notice that it's evenly distributed throughout the container. There's just many reds and blues all intermingled. That would be an example of a homogeneous solution. Okay? Number 3, pure substance or a mixture. Look at each particle. How do they compare to each other? They're exactly the same. This, again, is an example of a pure substance. Now, is this an example of a pure substance element or a pure substance compound? And hopefully now you're thinking to yourself, this is a compound because there is a atom that's a purple atom and a blue atom. So this is more than one type of atom bonded together. So this symbolizes a chemical compound. So this would be a pure substance as a compound. And if I were to separate them, I would get the 2 different elements that make it up. Here, when these separate, they're exactly the same spheres, so it's still the element but just broken apart and its bond is broken. Last picture down here, pure substance or mixture. Mixture, because we have different particles represented. Heterogeneous or homogeneous? Now, believe it or not, this is an example of a heterogeneous because all of them are isolated in one area while all the other ones are around that. They're not intermingled evenly, and therefore we have different phases. It might be like a solid inside of a liquid, and the liquid is surrounding the solid particle. So this is an example of a heterogeneous because we have different phases and different locations. It's not uniform. Heterogeneous mixtures are not uniform. Now, is it a colloid or a suspension? We need further evidence to be able to understand. We have to do the Tyndall effect, a shine line, and see what type of it is. All right, so this is a lecture on this material. This was covering in your packet on pages, I believe, 15 and 16. All right, so now after filling in the information there, I would like you to do page 17 as homework in your packet. And then if you go to Canvas after completing page 17, there will be an answer sheet for page 17 that you can look up and then check yourself to see how well you understand it. Once you're done with that, I then have 2 quizzes in Canvas I would like you to do on the last 2 sets of lectures. On classifying matter, which is this, and properties of matter, which was last week's. These quizzes you can take multiple times and try to get the best score possible on them, so please do. And those will be entered into Skyward next week and getting closer and closer to the end of this unit. Again, thanks for listening. If you have any questions, please reach out to me.